years and also blend in some of the industry perspectives that I gained while at ExxonMobil, as you mentioned. The focus is going to be on subaqueous landslides. We're going to kind of go through all the typical data sets that we would normally work on. Here on the title slide, you can see pretty fascinating just seabed image from the Gulf of Mexico, showing very recent slope instability features, very common feature, especially in the Northern Gulf, but broadly in the global scale, both in the modern day and in the deep rock record as well. So these are very common and affect a lot of deep marine sediment and margin evolution. Just to step back just a little bit and show you a little bit about what I do, although Tim mentioned the details already. I'm lucky to work with students and postdocs and other faculty at Ohio State, and I get a chance to work on some basically classic marine geology and geophysics type processes, even though I'm in the Midwest. Currently, I'm actually calling in from Barcelona, where I'm on sabbatical, so I'm visiting scientists at the Institute of Marine Sciences. So kicking off some new projects in the Mediterranean, which has been great. Yeah, so I do a variety of research topics, and today I'm going to focus on submarine landslides. I attack the problem sort of with classic techniques where we blend geophysical data to image and map deposits of submarine landslides. When we have the opportunity to collect in situ data, whether it be from physical cores or log data, we definitely will use and integrate those data sets as well. Often marine expeditions on ships or research vessels are at play, mostly through the ocean drilling program, and then some numerical modeling as well to understand the underlying physics. A classic image here that's often in the literature when learning first about submarine landslides, they're basically like landslides on the land surface. In other words, they're just gravitational instabilities, and they're basically combinations of sediment, what's ever there, and the seafloor is usually unconsolidated or unlithified sediment. On land, obviously, can incorporate rock as well. The scales are much bigger in the seafloor environment. These tend to be much larger and voluminous than the subaerial counterparts, but nonetheless, the physics are generally the same, where most of the work is being done by gravity. But there's a dizzying variety of ways in which these submarine landslides can move and then also be deposited. Some spectacular outcrops are often shown in many places. Here's just one example from Japan, where you see this exposed outcrop that has entrained some upturned blocks that are larger than humans. So the scales of these are quite impressive. This is relatively large for human scales, but these can get much bigger as well, both in the vertical dimension and laterally. Today's topics, I want to focus on basically the whole spectrum. I want to start with the pre-failure, sort of the source regions, and I want to look at the mechanical properties of the seafloor sediments in unfailed regions. And then I want to talk about the implications for those properties on how that dictates the failure or sudden failure behavior. If something's going to fail, it's going to be controlled in some ways by the properties that it had to begin with. And then finally, when it comes to rest and it becomes a deposit on the seafloor and incorporated into the rock record, it turns out that the mechanical properties of these deposits are also quite interesting to explore. And so we'll round out the talking about the deposits. So pre, syn, and post. This is a couple of examples from some of the work, and I'll show these later, but just to sort of get your mind looking at these things in seismic data, classic reflection seismic profiles. The top panel is from the Gulf of Mexico in the Mississippi Fan in a place called the Ursa Basin. This is a classic area of slope instability, and the industry knows this well because it's infamous for near surface overpressure that has plagued some of the development fields in the area, notably the Ursa and Mars development fields. And as a result, there's also a lot of slope instability in the form of submarine landslides. And this is a high resolution 3D seismic data set just showing one profile, showing some of these very near surface, so geologically young subaqueous landslides. Typically, you can see these classically by their chaotic and or semi-transparent seismic facies. And you can compare and contrast that with what's above and below that, these classic semi-parallel, more stratified facies that are the non-landslide, so hemipelagic drape in between major landslide deposits. This particular one in the Gulf of Mexico behaved rather fluidized, and it contains some chaotic facies indicating that it was well blended and mixed as it moved and failed down slope. The bottom panel is in contrast to that. So we're moving now to offshore Oregon, where we have a lot of active tectonics and particular seismicity at play. This is just one example. This is something called the 44 North Landslide. These triangular pieces are actual blocks of landslides. The source region is off to the right off of the slope. We're now out into the abyssal plain. But these types of blocks are only possible when you have very strong material that is being incorporated into the failure, much different than what we see in a place like the Gulf of Mexico. So that theme, what controls blocky versus non-blocky, is kind of a key question today. Thinking about earthquakes are a very important driving mechanism or triggering mechanism for slope failures, not only on land, but also under the ocean. Some of the more important historical examples are here on the left, the 1929 event from a magnitude 7.2 earthquake in the Grand Banks region and the Laurentian Fan. You can see the star here. Here's New England, US. Yeah, so the earthquake occurred, and then shortly thereafter, there was a tsunami that was probably triggered mostly by the earthquake, but amplified by subaqueous landslides and tsunami events. This is also a famous textbook example because of its rupturing sequentially of subaqueous telegraph cables that were laid on the ocean floor. And by the timing of the breaks and the location of the breaks, you can back out the velocity of these events. So this is one of the first examples where we started to realize how dynamic the seafloor environment was and how large and fast these types of flows can move across the seafloor, and also on very low slopes. Another historical example is 1964 in Alaska, the Great Alaskan Earthquake. Devastating example, even larger earthquake, and also devastating tsunami and associated subaqueous failures in many regions that people have explored subsequently with geophysical profiles and cores. I'll come back and show you an example later, but these are also very blocky types of landslides that occurred in this location. So we know, here's just a map now of seismicity or global seismicity over the Earth, and we know, of course, that they tend to be focused in the Ring of Fire in the Pacific Ocean, where we have active subduction going on, in contrast to more passive margins in the Atlantic and other locations. So right away, we should be able to expect, just with a first order hypothesis, that we would expect to see more submarine landslides where we have more seismicity, if earthquakes are such an important triggering mechanism, which they are. Interestingly, however, we actually don't see that. We see a kind of a puzzling observation where we have sort of the opposite result with more and larger submarine landslides occurring on passive margins, where we actually have very little seismicity at play. And so people started to see this in the early 2000s. There's a paper by Homa Lee, one of the first ones, that sort of saw this puzzle and then offered an explanation or term that he called seismic strengthening, which is a term I'll use throughout today, basically, and I'll show you what I mean by that several times. But in other words, seismic strengthening suggests that large swaths of the ocean floor can be actually strengthened over time if they're exposed to seismic shaking, given or provided that the seismic shaking isn't enough to actually cause failure itself. So it's this interesting zone in which there's enough seismicity but not vigorous enough to cause failure. Some of the field data to support that idea was taken here in Southern California, seismically active region. We actually have landslides in the area, as you can see by this map, the Goleta Slide and the Gaviota mudflow. But there is this section of seafloor in between these canyons and these slides that has remained relatively stable. And right here with this star location is a gravity core that was collected by the USGS. And in that core, they were measuring the shear strength of the sediments, and you can see 0. So this is seafloor. This is not that deep, so this goes down a half a meter into the subsurface. So just the first 500 centimeters. The circles here are the measurements made of the shear strength. So probably with a vane shear device directly on the sediments. And you can see they actually trend out here more or less linearly with depth, which is what we'd expect, although there's some complexity in the curve. But the key observation they made was it's offset from what we would typically expect a normally consolidated strength profile to look like, which is this black curve, which is a theoretical curve, but rooted pretty strongly in soil engineering literature and what we know about shear strength properties of normal marine sediments undergoing normal consolidation. So theoretical should be, but we actually experience this. So there's some enhanced strength that's unaccounted for. After these sort of early results or studies by Loma and USGS, some other groups have been looking at this question and doing a lot of field studies and just sort of doing an accounting or inventory of submarine landslides and where they are geographically. And sure enough, you see this interesting relationship that supports this idea that earthquake recurrence interval is inversely proportional to submarine landslides. So a plot of this is shown by this paper by Ten Breek et al. In 2016 in geology. So he's plotting here scar fraction. So scar fraction in these locations, both active and passive margins, as a function of earthquake recurrence interval or vice versa. So you can see the longer the recurrence interval, the more scars you have, which is the opposite of what you would expect, maybe typically. So this trend has been observed here in this sort of global study. There's been a variety of studies in other locations over the years, past couple of decades, that have supported this or seen similar observations, in which you just do a simple, observational analysis where you count up submarine landslides. They're more or less easy enough to identify with standard seismic data and or seafloor data. So you can do a pretty good job of counting them and simply compare those with passive margins to get an idea of, are there a lot, are there few? And so over the years, the field has documented this interesting relationship. The general idea is quite simple. It just suggests that if you take the same sediment and put them offshore North Carolina or a passive margin and let them consolidate normally, take that exact same situation and put those offshore Oregon or an active margin. The only difference is that one is exposed to seismic waves over time, or, through the first 100,000 years or so of their gravitational, or I should say burial history. That additional wave action is going to shake in and dewater the sediments as they are also compacting. So you get this additional density or densifying mechanism. So this is the original idea behind this seismic strengthening hypothesis. This is not too outlandish. This is an interesting little video that you can see on YouTube and a lot of places. And I just want to show this just as a visual demonstration of this process. And it's basically liquefaction in situ. In this situation here, these guys have a small tank with sand, and sand is common, although the deep marine is more mud. But just to illustrate the process here, right? They're putting some houses and cars, and now they're shaking the entire system, and there's water in the pore space in that sand. And over time, you can expect to see what will happen. That shaking is causing the grains to rearrange, and water is going to be percolating up into the surface sediments. So there's no water added to the system. It's just been rearranged. And now you can see it causes, of course, major problems to the surface. But what I want you to take away, of course, is that water that's now on the surface there has been expelled from the pore space in the sediments. So the sediments are being densified as that near surface water is increasing and causing problems. So this idea is interesting, has some merits. And then the USGS started to play around with, okay, can we actually do earthquake shaking in the laboratory on natural sediments, marine sediments? And I just want to show you one example of this. It's kind of a cool experiment. So what they're doing is they're taking basically a standard hockey puck sediment sample or specimen in a ring on the order of a few centimeters in diameter and centimeter or two thickness, so small scale. And they're conducting an undrained shearing experiment while exposing the sample to bursts of cyclic shearing to mimic earthquake shaking. And the shaking is done in an undrained fashion. So actually during the earthquake, it's actually not allowed to drain off those fluids which is more what would happen in nature in marine muds because of the permeability is so low. You can't drain off that water like you can in the sands in that video that we just saw. But after the earthquake episode is done, then they open the drains and let the sediment dewater if it wants to. And sure enough, you can see that it does. The plots of this here are showing the void ratio. So this is porosity or void ratio, high void ratio on the top and low to the bottom. So as the black line goes down, that means that sample is consolidating. The deviations to the left and back to the right are these cyclic bursts. So we're looking at the effective stress on the horizontal axis. So every time it goes to the left, the pore pressure inside the sediment is spiking, and then it bleeds off. And then as it bleeds off, though, the sediment consolidates in situ. So a really neat experiment. And after they did that, they measured the strength of the sediments as a function of effective stress or number of earthquakes. And here in the right-hand plot, you can see that. So at the beginning, it has a static shear stress of whatever it is. And then after being exposed to these laboratory simulated earthquakes, the shear strength of that sample, because it's densified, actually has gains of strength. So interesting proof of concept here that kind of demonstrates, at least in the laboratory scale, that this process occurs or can occur. I often equate this to James Bond's martini, shaken, not stirred. So the idea is if this happens in nature, you can shake the sediments and actually, enhance their stability over time. But if you shake them enough, you can actually stir them, of course, and cause a landslide. Where I come in is where I wanted to test this in the field data and see, okay, if the shear strengths of natural sediments at natural scales and natural environments actually are able to record this or suggest that this is actually happening. So take it outside the laboratory world and see what we can see with in situ data. And thankfully, we have a large data set to work with. We have over 50 years of scientific ocean drilling through the Ocean Drilling Program and its predecessor, the Deep Sea Drilling Project, and now it's called the International Ocean Discovery Program. But the idea is the same. Every dot on this map represents a location where the drill ship has gone in and extracted cores. And one of the standard measurements that's always taken or almost always taken is the shear strength of the sediments in regular intervals down core. And all that data is nicely preserved and archived, publicly available. So what I want to do is go in and just basically do a data mining exercise and see if we can see these patterns of strengthening in actual field measurements. So the idea is pretty straightforward. We just basically data mining the available data from the archives. And what we're looking at are measurements of shear strength taken by the same exact tool, the automated vane shear device, which is basically a 4-bladed paddle that inserts into the open core face. So the cores are collected, brought up to the ship, they're split open, and then one of the first measurements is this AVS or vane shear measurement taken on the core at regular intervals. And as the blade is inserted, it's then rotated until breakage is occurring. And so we can measure the stress strain curve throughout that experiment, and we can record the peak shear strength or resistance of that sediment and record that as a function of depth. So we're going to look at those data sets. And only thing I did was just focus on the upper 100 meters of seafloor sediments, because this is where landslides are going to be occurring if they're going to occur. So we call that the landslide zone. So anything deeper than 100 meters is kind of too deep to be interested in. And I also wanted to focus on siliciclastic environments and not get too focused on carbonates or have carbonates at play here, just because of their very different mechanical behavior. So I'm restricting my data analysis to those types of materials. In the end, let me go back. We had a total of 2,500 shear strength measurements. Half of those basically turned out by coincidence to be just about half and half between active margins and passive margins. And that's the only thing we did. We just bin them. Are they on a passive margin or on the active margin? And then we sort of just plotted them up and saw the results. So I'll just show you quickly. This is one of the first results you get. These are just unfiltered data, just the raw data sets themselves. And sure enough, you actually see, even without any work or analysis or filtering, just with your eyes, you can see that the red circles are systematically offset to the right, indicating higher shear strength, mostly with depth. There is some overlap, of course, but if you look at the distribution of the data points, you can see a systematic strengthening. So if seismic strengthening has nothing to do with this, and maybe this at this point we don't even know what's driving this, but we can observe a clear offset in the shear strength data sets. Now, there is a lot at play here in those data sets. We have not done any work to look at prior failures, interesting chemistry, anything mineralogically that would also cause a spike in shear strength. And that's one of the key things we had to really spend time on in this study, is taking those raw points and really trying to understand, okay, are these valid apples to apples comparisons, or are we just looking at differences in lithology or cementation effects or other things? And so this is just a list of things that can affect that measurement of shear strength, that vane shear measurement. You can think about effective stress. So if that sample comes from a high pore pressure, Mississippi fan type environment, and we take that up, it's already going to be softer than maybe normally. If it's got different lithology or mineralogy components, if it's got cementation or gas or hydrates, if it's been bioturbated, that's going to be a major impact on shear strength. And depending on whether or not it's already been unroofed by prior landslides, or if it itself is a deposit of a landslide, it's going to have very different shear strength profiles. So we had to go in site by site and rule out any of the sites that had any of these factors that would complicate the shear strength comparisons from active and passive. And in doing that, so we had to go in and say, okay, let's look at only the areas that have these things in common. So we want continuous sedimentation and burial, as simple as possible. So layer cake geology. And it turns out the paleoceanographers who design a lot of their cruises are also looking at sites that have those types of characteristics, very layer cake, simple geology. So actually, a lot of the ocean drilling program cruises have these types of relatively simple sites to choose from. We also need to know that there's hydrostatic pore pressure to make sure that things are not overpressured. And we want to make sure, based on seismic data or site survey data, that there's no evidence of major unconformities or unroofing. There's no prior landslide deposits, and no, as best we can tell, no cementation or gas hydrates at play. And when we did that, we were left with these 8 total sites that emerged from that more global data set that are more apples to apples type comparison. And the idea, what we want is same types of materials, same types of burial depths, same types of stresses, and really the only difference is that it's located on a passive margin or an active margin. That's kind of the goal that we were looking for here. So you can see the red stars are the active margins, and the blue stars are the passive margin sites. So you can see Atlantic margin, Gulf of Mexico, Amazon fan, West Africa, and then we've got some samples offshore Japan, Pacific Northwest, and also the Mediterranean. Now we're doing the same plot here. You can see the cloud of data I showed before is now these 8 sites all co-plotted together on the same plot and connected with lines. And you can still see even more clear now the systematic offset in these active margins, the red sites, relative to the blue sites on the passive margins. So shear strengths are systematically higher by a factor of 2 or 3, so twice as much shear strength for a given depth or effective stress, which is quite significant. So this is a pretty cool demonstration that in these sites you can see the active margin sites are in fact stronger than their passive margin counterparts. This is consistent with the seismic strengthening hypothesis, but there could be other factors at play here as well, but certainly compelling. Now, after seeing this, some thought questions emerge here. So what about places where we have overpressure? We care about those places because those are also going to be the places that are prone to subaqueous landslides, low effective stress like the Gulf of Mexico. So we kind of want to know how this seismic strengthening is going to play in a place where you also have high overpressure. Well, what happens at deeper depths? Do these strengths come back and converge again once you get deep enough where there's just too much porosity loss for earthquakes to cause any more densification? What depth does that occur at? The offset in these strengths seems to be smallest closest to the seafloor. As you can see these curves almost converge at near zero seafloor depths, and then they quickly diverge from each other. So what happens there in those early histories? Can we then look at each site and understand the earthquake histories at each site to gain more information about or insights into the control of earthquakes? And can we recreate the burial and seismic shaking in the lab of these exact samples to further test the hypothesis about seismic strengthening? And we'll come back to these questions here throughout the rest of the talk. I want to transition now to this question of what happens when we combine both high seismicity and high sedimentation rates because they're counteractive. You know, if you have higher sedimentation rates, enough to have high overpressure, then you will have more submarine landslides. On the flip side, as we just saw, if we're just in a normal open marine slope, maybe with not a lot of sedimentation, but seismicity, we're going to have a strengthening effect going on. So I wanted to look at a place that has both of these going on, both high seismicity and also high sedimentation rates, and see the strength profiles and see sort of what wins out or how they play together. And one of the places that emerged as a good test location is this area offshore southern Alaska, southeast Alaska, where we have a very large underwater fan called the Surveyor Fan that's collecting or receiving all the sediments that are being shed from the coastal mountain range here, the St. Elias Mountains. And so there's a lot of sedimentation being derived from these coastal mountains that are being funneled out into the deep ocean by these submarine channels. And so this big fan is being built over time. And so we have the opportunity to see seismically active plate boundary, and then we have a high sedimentation fan on top of it. And these red stars are the locations of an IODP cruise that went in systematically cored this profile and of course measured shear strength. So I'm going to look at the shear strengths of these sediments, and it turns out they're quite well-behaved sediments in terms of well-behaved being in light of this particular study, in that they're nice mudstones. They're very similar to the materials that we were just looking at in the previous part of this study. They have overpressure because of the high sedimentation rates. And so we have all the ingredients at play here for this type of question. Let me just fast forward right to the results here. You can see the plot on the left is what we've been looking at before, where we have depth on the left or the y-axis, and these peak undrained shear strength measurements coming directly from the cores on the x-axis. There's two families of data plotted here. The first, this cluster, is the actual measurements made on the red stars. So you have 14, 17, 18, 19, and 21. Those are all plotted here. The thick black line is the composite of those four sites. So it's basically treating all four sites as if they were one Surveyor Fan site, and sort of just sort of making a composite. The one on the right is interesting. This is coming from outside the Surveyor Fan, and site 887 from an older ODP expedition made on the Patton Murray Seamount chain. So this is technically outside the Surveyor Fan, but still on the seismically active part of the plate. So it's still receiving seismic shaking. The key difference, though, is that it's not overpressured and it's receiving much lower sedimentation rates as a function of time. And even though it's just one data point or one profile, it does systematically sit significantly to the right of the Surveyor Fan sediments. So in other words, the lower sedimentation rate sediments are seismically strengthened. So outside the fan, you get almost all seismic strengthening. And inside the fan, it's not clear what's going on. Is this normal shear strength development, or is this actually mostly controlled by the overpressure? And to gain insight into that question, we come back to the global plots that I've shown before from the previous exercise and sort of shown them relative to each other. The red sort of field or zone that's colored in the background are all the active margins, or the ranges of the active margin profiles that you've seen before. And then the thick one on top is this site 887 outside the fan. So that actually fits nicely within the band of active margin sediments. The Surveyor Fan sediments are the ones plotted here that actually fit within a passive margin profile. So they're behaving interestingly like a passive margin profile would be, normally consolidated passive margin profile, even though they're on an active margin sediment. So they should be seismically strengthened, but they're not. And we think this is due to, you know, the high sedimentation rates and overpressure that we have in this growing, fast sedimenting fan. The last profile that's here is the Gulf of Mexico. So this is that Ursa basin that I showed earlier. Very high sedimentation rates, but relatively low seismicity compared to southern Alaska. So you don't have any seismicity at play here, but you have very high overpressure. And I show that just to show that, you know, the Alaska Surveyor Fan sediments, they're weaker than maybe their seismically strengthening could get them, but they're not as weak as, say, a Gulf of Mexico, so an overpressured, you know, deep sea fan. So I think this could be showing that there's some strengthening occurring. So there's a little bit of strengthening occurring, but that the overpressure is also not allowing it to be strengthened enough. Yeah, back to the Mississippi Fan, Gulf of Mexico. Ursa Basin. We know these locations are very, very high overpressured in the near surface. And this is the image I showed on the title slide. And you can see a profile on the subsurface across this line. You can see there's seafloor failures already, but let's look into the subsurface. And this is where we see now the recent history over the last 100,000 years or so that's shown in this image is replete with submarine landslide deposits. So everything colored in this brown is a mass transport deposit, and we've mapped these from seismic data, and we've cored them with traditional piston cores and logged them with logging while drilling data. So we know their properties quite well. And you can see, let me just go back once, you can see most of the seismic facies, when you map these things out, they're relatively thin and they're far-reaching types of landslides. So they're starting from weakened materials, and because they're weak when they start out, when they go downhill, they tend to fluidize and make long run out, relatively thin types of landslide deposits. Okay, let me fast forward here and think about this question about the landslide behavior itself. So we focus now on the pre-failure properties, thinking about seismic strengthening and what happens when you have overpressure at play. I want to examine this question a little bit more about what happens to those landslides if and when they do occur, if they start out relatively strong or relatively weak. So in the pre-landslide, in sediment-starved regions, we can argue that seismic strengthening appears to help stabilize portions of those margins, which means that you would need a larger earthquake to cause failure. In the post-landslide, even in strengthened sediments, you can still get a large enough earthquake to shake those sediments loose and cause a slide. We would then expect, therefore, the behavior of such a landslide coming from strong materials is going to be very different from those that are not strengthened, or in fact weaker, perhaps like the Gulf of Mexico. So I want to take you to the laboratory now, where we can play around with mixtures of materials and make or simulate, real muddy type seafloors basically, and cause subaqueous landslides in the laboratory and make detailed measurements. This is part of my PhD work at the University of Texas in Austin. It was a fascinating time to be able to make landslides. And what I did was I systematically varied the starting properties and kept everything as constant as I could. So relevant to this talk, we can think of these things as I'm controlling the strength properties by controlling the porosity or the void ratio. And I'm keeping the triggering mechanisms and everything else the same. And I'm just examining the differences in the dynamic behavior and also the deposit morphology and geometry characteristics as a result. Here are just some pictures of those experiments. You can see what you're looking at here. Let's just start with the left, top and bottom. These are weak materials, and you're looking at the side view of a flume, basically, that's sitting in a aqueous tank. And the materials are fine-grained mixtures of clay and silt, so mud, basically. There's no sand in these systems to mimic more deep marine sediments. This is after a landslide has occurred, so you're looking at the source area where things have dropped. You can see this line that goes across. I'm drawing with my mouse. That's the original height, which is 10 centimeters thick. So these things are 10 centimeters thick. They're about 75 centimeters long in the longest direction, and about 20 centimeters in the other direction. So tabular sedimentary deposits. So after this weak one was able to fail, it lost a fair amount of material. Where that material went, you can see in the bottom panel, it comes out of the gate. So you were looking through this window to this tab. That's this view on top. And then as this sediment failed, it went down the pool slope. This is a 10-degree slope in this dark, it's like a wedge basically on the bottom of the pool at 10 degrees. And then it flattens out to the pool bottom here at this break in color. So 10 degrees to 0 degrees. You can't actually see the deposit. It's under here. I've dashed it in here. It's growing basically as when this picture was taken. But at the same time, there's this cogenetic large turbidity current that basically got shaken loose as the material, vigorously left the source area. And the way I'm making the landslide here is there's a door here that you can vertically remove. So before the landslide, everything is contained within a box, and then I just remove the front gate kind of instantaneously, and then the system can unravel as it wants to. Now, of course, that's not really representative of natural triggering mechanisms, but I was interested mostly in the post-failure behavior, not so much how these arrive at failure, but after failure starts. So yeah, you can see this is the weak one. Then we can ratchet up the strength, same material, same everything. All we've done is made the same mixture, but dropped the porosity or water content by a little bit. And you can see as you do that, as you might expect, what happens is that the material gets stronger and it's more able to resist those static driving stresses. And the material, a lot of material stays in the source area. If it does start to strain, you can see these fractures, really beautiful fracture fields develop. And the stuff that does get out slope or get down slope, it doesn't reach nearly as far as the weakest stuff. It kind of grows. This is a interesting experiment because this one turned out to be really long-lived, more like 10 minutes of constant slow motion type of creeping before it came to fully rest. And then finally on the far side, we're basically at the limit here, where the sediments are so strong that they're almost able to withstand all of the static stresses even after lifting up the gate. You can see some slump blocks that occur just at the front, and there's some deformation that occurs back, but even once you get halfway back, there's basically no deformation occurring in the back half of the sediment deposit. Okay, so key point here is that, as you might expect, the pre-failure properties of the sediments exerts a really first order fundamental control on the style of the landslide and also on the deposits themselves. Like if you think of this as a landslide or a seafloor landscape, and you have multi-beam data sets or seismic data sets, you can imagine seeing these types of material or geomorphologies, I should say. And the point is that these morphologies are diagnostic of the failure deposits. So you can gain a lot of information about the failure behavior just from the deposits themselves. In that tank, you can also then do post-failure measurements with detailed line scans, measurements of the topography, and map them three-dimensionally to do basically, what you would do with geophysical data in the natural systems. So you're looking at now the profiles of the source areas, and you can see, as you might expect, and as I showed before, the weaker they are, the thinner they leave behind. So most of the material in this example B here, the green line, most of the source area thickness has dropped from 10 down to 2. So 80% of that height is gone, and it's left now into a deposit. And you can see the stronger you get, the thicker it remains, and also the more fractured you make that margin. The deposits themselves, you can see the trends are also what you might expect, in that the weaker ones travel the farthest downstream. They're the thinnest deposits, and they also spread out laterally more because they're weaker. One last sort of insights that we can gain from this is doing volume balances to figure out where material goes. So how much, how fast type of a question. We're plotting here the volume released in these 3 types of experiments as a function of time. And it turns out that the weakest experiment is also a short-lived experiment. So it's only lasting a couple of minutes in the laboratory because everything is happening so fast because it's so weak. The same is true for a strong one here. It only lasts a couple of minutes, but it's not going very far. Most of the stuff stays in the source areas, 90% versus 10% source to lobe. And then once you're in sort of the sweet spot in the middle, you can actually get these long duration styles of runouts in terms of time. So instead of 2 minutes, we're now going more than 10 minutes for these middle type of experiments. So these are like these retrogressive failures, at least in the laboratory environment, that can have these long-lived types of deposits. So interesting duration effects here going on. Okay, putting all that together, we can actually quantify and make predictions about the type of failure behavior if we know something about the pre-failure properties. This is where it comes back to the key questions about pre-failure properties controlling the dynamic behavior. So in this plot here, it's kind of busy, but what we're doing here is we're plotting something that I'm calling the flow factor. So these gray zones, dark gray to lighter and lighter gray, are going from just arbitrary 1 to 7. What that means is, if I have a flow factor of 1, it means that I'm basically at static equilibrium. My driving stresses and my resisting strengths are basically equal. So the ratio here is 1. As I make the materials weaker and weaker, the shear strength, the resisting shear strength, the denominator gets lower, even though, so tau d stays the same. So this whole ratio gets higher and higher as my resisting strength gets weaker. So the weaker the sediment, the higher the number here. So in other words, as I go in this northwest direction, I'm starting out with weaker and weaker properties. And you can see that because I'm increasing water content on the vertical axis, increasing porosity on the vertical axis. You can also do that by just changing the lithology. So clay size fraction here, if I make it more clayer, it tends to make it more thicker or more higher shear strength. If I make it less clay and more silt, that can also drive the system to a weaker starting situation. But for today's topic, we're thinking just in terms of water, amount of water, and the effect of seismic strengthening means that, for a material here that starts out here, over its geologic time, it's getting exposed to seismic strengthening. It might otherwise be a factor of 5 or 6 on a passive margin, but we can now drop that to something that's going to be a flow factor of 2 or 3. And what that means is the style of landslide, as I just showed you, can go from something that's more weak to something that's much more stronger. I'm just sort of cherry picking here some examples of that. There are exceptions to every rule, of course, but it does seem to have some merit here. So you look at one of the more famous ones, largest ones on the Atlantic side, at least on the U.S. side, is the Cape Fear landslide, a series of large landslides on the Atlantic margin. You can see it in the modern day seafloor. So the Cape Fear landslide here is the one to the south, offshore North Carolina. We also have a couple of large ones to look out in the Currituck as you go north. You can zoom in on the Cape Fear slide in the top plot here with some side scan sonar images. Bottom line is these materials are, when they release, they fail and they go very far out into the abyssal plain, and they're very thin deposits. What's triggering these landslides is still a question, still a mystery, but the bottom line is the resulting deposits and failures are much weaker. So in other words, they're starting out as weaker materials. They don't have seismic strengthening to help them get stronger, and as a result, they fail in a fluidized type of a manner. Back to something I showed earlier, if we go to another place offshore Oregon where we do have seismicity at play here, we can see this blocky, very blocky style landslide, completely different from what you just saw at Cape Fear, where you had these 100-meter plus tall, very angular type blocks that are coming from this cookie bite in the slope here. And so these blocks are imaged down in the profile below. So yeah, 100 meters tall from the surrounding seafloor, and there's several kilometers worth of blocks littered on the seafloor. Their impact forces are interesting. They're causing this deformation that you see out in front of the blocks, which is another story. But it turns out that what we know about the margin strength profiles here are they are in fact stronger. Again, coming from ODP data, if you can see in this map here, this red star, this is offset by 50 or 60 kilometers from this actual site location, but it's the nearest data set that we have, shows that the shear strengths are in fact higher and plot very much within the active margin zones that we would expect. There is also hydrates or evidence of hydrates in the source area, so it's a little bit more complicated than perhaps just seismic strengthening. But bottom line is you can see much blockier style landslide here. Now, the implications for things like tsunami size and amplitudes, it gets complicated because the larger, blockier landslides actually are more tsunami-genic or can amplify tsunamis, generally speaking. But if you have very fast-moving, large volume landslides that aren't necessarily blocky, but they have a lot of momentum, you can also get a large tsunami. So there's not a simple rule to say that these are more dangerous or not than active margins, or passive margins. But nonetheless, both can be. We also see these blocky styles of landslides in the area affected by the 1964 Great Alaska event that I talked about before. These are revealed with high-res multi-beam images and some work done by the USGS to show that that earthquake shook loose a lot of materials, landslides, and those landslides were quite devastating in terms of the coastal tsunamis that they created. Okay, do a quick time check here. Let me sort of wrap up and just sort of talk quickly about some of the current work that we're doing as we speak. So back to this question of the increased strength, I don't think we've sufficiently demonstrated that it's all due to earthquake shaking or the seismic strengthening hypothesis, but certainly it's been compelling and interesting enough. So I've been able to get some additional funding and support to do some more detailed studies And there's a picture of Bailey Fitzgerald. She's a PhD student with me at Ohio State. She's holding the letter, but behind her is these samples, these exact samples that I've just shown you in the previous analysis about, these materials are representative of seismic strengthening samples or passive margin samples. So we now have those samples in the laboratory where we're able to really understand everything about them. We're going to do detailed sediment characterizations, their grain size, mineralogy, their physical properties, their Atterberg limits, and engineering properties. And we're also going to do resedimentation tests. We're going to start Mother Nature over. We're going to take them in the lab and start them from basically zero stress, mix them up sufficiently so they're all starting from the same starting water contents, and then stress them to the exact same vertical stresses in the laboratory, and then measure their shear strength and see how alike or different they are from the field measurements that we've seen already. So kind of a fun project that we're just starting now. So pictures of the first steps of this are getting hands dirty, looking at grain size and classic settling tubes here on the left, Atterberg limits here in the middle, and some more grain size pictures here on the right. Mostly clay, but there is some bits of sand that we see from time to time. And just some quick pictures from resedimentation experiments, which we've just started this past summer and just wrapped up now. This is in collaboration with Julia Reese in her laboratory at Texas A&M, where she's able to do resedimentation experiments. So this picture is of one of the 8 sites that I've shown before, and it's being resedimented now. And you can see it's basically on its way to becoming a hockey puck, which will eventually shear in the lab. I can show you some preliminary data, relatively hot off the press, emphasis on preliminary here, but I do want to show you because it's kind of interesting. If you look at the void ratio, these are the compression curves for 3 of those samples, North Carolina, Nankai, and Amazon. So you have 2 passive and 1 active in this case. We're plotting them out to 100 kPa, which is what we get from the resedimentation in the lab, and then we'll further consolidate those in a true consolidation cell later to a full megapascal of effective stress. But here out to 100 kPa, they converge almost to the same void ratio at the same stress, despite having different shear strength properties as measured in the field, sort of in situ properties. So when we take them back to the lab and sort of reset their geologic fabric, we actually see they're quite similar, behave quite similar. So we still have to stress these, and then we still have to expose them to shear strength measurements, but some really interesting and exciting results all coming out so far. And then eventually, in a couple of years, we're going to return to some of the stuff that the USGS pioneered, where they were exposing these materials to seismic shaking. And so what I want to do is take those exact same 8 samples, and after we do the consolidation and shearing, is then expose them to systematic shaking in the lab and really understand controls of lithology and different types of wave spectra on this seismic strengthening effects. Does it matter how fast, how much, in terms of the amplitude, what stress ranges are going to have the most effects? Really try to understand these processes at a greater detail. Okay, last sort of look here is back to sort of maybe applications for industry type projects. Back when I was working for Exxon and just part of my grad school training, working for Shell and BP and shallow hazards or deep water environments, one of the things that was observed is that the deposits now, once you fail something and they're left on the seafloor, they also have this interesting property of enhanced porosity. They're densified relative to more hemipelagic drape style sediments. So you see this, there's a Gulf of Mexico example that I've been showing you before. There's also Amazon Fan here to the right. MTD stands for mass transport deposit. So that's sort of the jargon term for anything that's deposited as a mass transport event or submarine landslide event. And we're looking at porosity as measured directly on the cores here. And yeah, you see this very common throughout many MTDs that have been sampled, is they have lower porosity than what's above and below it in non-landslide materials. So is this inherited? Is this from the early burial phase, perhaps from seismic strengthening, or is this porosity related to nothing to do with that and has everything to do with the function of the failure processes, the transport, and then the consolidation effects after it's been sitting on the seafloor and then buried? I think it's clearly more the latter, that this is not a function of the pre-failure. The pre-failure seismic strengthening type porosity is definitely going to have a say in how this MTD moved it down slope. But unless it doesn't internally shear and it just sort of translates down slope, that porosity is going to be a function of the internal shearing and the post-failure compaction processes after the fact. But if it does move down slope as an intact block, this porosity profile would result, or Sediment would represent and reflect that pre-failure porosity. This is important in some situations in the quote unquote foundation zone for deep sea wells and foundations for suction anchor piles. This is for deep sea wells. You can think of anything that's embedded into the seafloor. This could lead to non-productive time. If the material that is being jetted into is stiffer, perhaps they're seismically strengthened, perhaps they're MTD deposits, they're going to have a longer installation time. So there's some NPT or non-productive time effects here at play. This is shown really nicely by a paper from Craig Shipp way back in 2004, where he's plotting, going through MTCs, and the average penetration rate of suction anchor piles here in the red takes about 13 hours to go the same depth, 80 meters or so, as you would in an area that doesn't have any MTDs. So understanding these properties and where the deposits are and where they're not does have some importance for shallow drilling activities. It also is potentially at play in the deeper intervals where you go through MTCs, maybe much deeper depths. It's not clear if any of the issues. So you can see some examples here. I've just shown two from literature that I know about. Offshore Angola, for example, where there's a lot of MTCs and noted drilling issues going through these MTCs to the point where, designing well paths, really trying to avoid time within MTCs. It's not clear to me if it's driven at all by mechanical properties or more chemical properties of the MTCs, but I just wanted to show this because there's this question about how the shallow rock properties of these mudstones evolve with burial depth. And so as we get more to more true reservoir type depths, how are the properties of those MTDs controlled by their early burial history? Some of the things I've just been talking about today. Okay, great. I am finishing up here with some of the key points that I've talked about today. Just real quickly, I've tried to show that active margin sediments have a systematically higher shear strength. We've looked at the top 100 meters to show that, relevant to more landslide studies. I've shown that you can do seismic strengthening in nature, but you have to account for, or can be counteracted by, areas of high sedimentation rate. So there's this competition between overpressure development and the sediments. And so if you have overpressure, you're not going to have as much seismic strengthening. Implications for those, just a few here. This earthquake shaking, if it can densify the sediments, it's going to have a stabilizing effect on large scale areas of continental slopes, back to what was earlier seen by USGS colleagues. If a landslide does occur from these materials, then the style of that landslide is going to be affected by those properties. In particular, if it's seismically strengthened, if it does break loose, it's going to be perhaps tend to be more blocky and more viscous style of failure, and vice versa. Regions that have both high seismicity and high sedimentation rates, such as Southern Alaska, I think are arguably the most susceptible, most sort of quote unquote dangerous for these submarine landslides and tsunami type hazards, because you have weak sediments and high shaking intensities. And then finally, these compaction models, thinking about these properties with depth and what's normal and what's not. I would say, way back to Athy's law, or exponential curves for consolidation profiles. We may be moving to an area where we kind of need to consider potential overconsolidation driven by seismic strengthening type effects on consolidation or compaction models in places that have seismicity, of course. So active margin profiles versus passive margin profiles. Something for future work potentially. Okay, real quickly, I just want to show you what I'm working on as we speak in the last few weeks, working on some work offshore Japan and an active margin. Again, looking at shear strength properties in an active margin setting. And then as I sit here in Barcelona, working in the Mediterranean on some really cool volcanic clastics, so things that are derived from volcanic activity but are now sitting in abyssal plain sediments. I'm able to examine their properties as well in light of seismic strengthening and other questions as well that I'm pursuing. Okay, last slide here is just some acknowledgements. A lot of people, a lot of funding support that have plugged into all the stuff that I've shown you today. I won't list them just for the sake of time. And with that, thank you, and happy to take questions if there is time. Thanks.
Hey, thank you, Derek. Fantastic talk. Quick question. Steve Davis asked question about seismic dewatering and increased shear strength. How does the square with liquefaction-induced damage, such as experienced in the Marina District of San Francisco and other locations like Mexico City, the initial response is pore pressure increase and sediment dilation with reduced shear strength, which is responsible for a lot of damage. Is the Marina District mudfill now stronger post Loma Prieta?
Yeah, that's a really cool question. Thank you for asking that. I don't know if I have a definitive answer. I am aware of those issues and those locations. Yeah, that's a really good question. I would want to, so I guess in the long term, you might expect there to be some increment of strengthening, but there's that water, I guess, is getting, as it's getting expelled from the sediments, is likely causing the liquefaction and subsidence issue. So I guess in the geologic timescale, it's doing what it's doing, but in the human timescales, it's a major problem. And yeah, but you know, that's just the first off the cuff sort of answer. There's a lot of interesting questions and processes at play there. But yeah, that's very, very relevant question. Thank you.
Yeah, and then a follow-up from Steve on the AVS measurements. How do you account for local compaction around the four-blade vein when it's inserted and displaces sediment volume laterally?
Yeah.
Compact the core material.
Yeah, exactly. We can't is the short answer. And so what we rely on is we're doing the same exact experiment. And so we're trying to keep that constant, hoping that the effects are gonna be in the quote unquote noise. But it's an important question. I don't think there's really been any systematic studies on those effects. I like the idea though. I like the question. And the other thing is we do see these effects though, like as the cores that are stiffer, like they come from deeper depths, and when we bring them up, they tend to be obviously more stiffer, and so they break or they naturally will crack. And so when we're doing a vein shear measurement on those, you really got to be careful on where you're putting the vein shear. Obviously, if you put something in something that's already been fractured, you're going to get an artificial measurement. But even if you're looking out for this, at some point, as you get too deep in these cores, these AVS measurements are really unreliable. And if you plot them up, which you can do, there's a lot more scatter and overlay. And I think that's mostly due to these measurements not really being reliable when you get that brittle there. But in the top 100 meters, top 50 meters especially, those effects are at play, but I think they're overwhelmed by other factors as well.
And then Jack Taylor asked, often a point of discussion is whether buried MDTs make good or poor seals for hydrocarbons. Any comments on that based on your research?
I would say my first reaction would be that I would expect them to be good seals. In other words, because they have reduced porosity. That'd be my first sort of general rule of thumb. I'm guessing there are plenty of examples where that is violated, perhaps if you have enough sand in the system. But if they're mud rich and if they've been sufficiently sheared, I would think that a lot of them would tend to be more better than not good in terms of seals.
Okay. A question from John Suppy. I'm interested in distinguishing seismic compaction from shallow overpressure development. I'm thinking of the drilling at Barbados. There is a 100-meter boundary layer of reduced porosity, increased cohesion, followed by slow variation. I had thought would be a fluid retention depth. I guess more of a comment. But.
I was trying to see, is that in the Q&A, that question?
It's in the chat.
In the chat. I think I followed, but let me just see real quick here. Seismic compaction from shallow overpressure development. Yeah, okay, cool. drilling at Barbados, 100-meter boundary layer. John, if you're still on, is the 100-meter boundary layer, that's 100 meters depth, or is it 100 meters thickness of the layer? If you're still on, I'm not. It's been a while since I've looked at the Barbados. Yeah. Yeah, I don't probably have a good comment on that.
And a follow-up from Steve, MDT can be a great or terrible seals, much depends on from where they are sourced. I've seen both.
Excellent.
Cool.
Yeah, if there's anybody that would like to work and partner, you industry guys have all the cool data. Once I left, I knew that was going to happen. But yeah, there's some, I'm sure there's some amazing examples, and I have what I can have, work on through public data and ocean drilling data, but I am sometimes jealous of the industry data.
Well,
Great.
fantastic. I missed one. The x-axis was just referring to offset distance. I guess that was earlier. Yeah.
Yep. I think if that's the laboratory experiments, I think that's what it would be. Yes. All the other x-axes are probably shear strength. Yep.
Mm-hmm. All right. Well, I'm gonna say thank you. We got to cut it off here, but Derek, thanks again for a fantastic talk. I'll be sure to pass on any additional comments that are or questions that are saved in the chat.
Great.
Anyone who has more interest, feel free to reach out to Derek with questions. Thanks again, everybody. Have a great day.
Great. Thanks, Tim. Thanks, everybody.